Hey, you probably remember the ideal gas law from school, right? It's that neat, simple little formula. But what if I told you it's actually built on two fundamental, well, lies? Today, we're going to dig into the story of how one scientist's brilliant reality check completely transformed how we see the physical world.
So let's just start right here with this question. Science is always talking about ideal this and perfect that, especially ideal gases. But what if that whole concept is just a myth, a really convenient simplification we made up just to make the math a little easier?
Well, it turns out the ideal gas law really is built on these two elegant but totally flawed assumptions. First, it pretends that gas particles are just these tiny, dimensionless points floating around in space, taking up zero volume. And second, it assumes these particles are flying around completely ignoring each other with absolutely no attraction between them. But as you can see here, we know that's just not how the real world works. Not even close.
Okay, so to really understand the fix, we first need to appreciate the beauty and, the flaws of the original. So let's start with that perfect gas myth.
And here it is, the famous one. PV equals nRT. I bet you've seen that 1,000 times. It's this beautiful little equation that links pressure, volume, the amount of gas, and temperature. It's simple, it's elegant, it's powerful, and, you guessed it, it's incomplete. Look, this law works great, but really only under very specific conditions, like super low pressures and really high temperatures, where those two lies we talked about are almost true.
So, if the ideal model is flawed, who was the scientist who was brave enough to say, hey, let's get real about gases?
This is our guy Johannes Dieterich van der Waals. He looked at that elegant ideal gas law and he asked this profoundly simple but totally revolutionary question. What if we just tweak this formula to reflect how gas particles actually behave in the real world?
And that is exactly what he did. So now let's break down how van der Waals corrected this famous equation for reality one piece at a time.
And what's so cool is how he did it. We're not just going to flash the final, complicated-looking formula on the screen. No way. We're actually going to build it together, piece by piece, starting from the original, so you can really see the genius behind his logic.
So his first correction, it tackled that whole volume lie. Think of it like a dance floor, right? The actual space you have to dance isn't the entire room. It's the room minus the space all the other dancers are taking up. Van der Waals realized the exact same thing is true for gas particles. They have real size, they take up real space.
And boom, here's the fix in action. In the equation, we just take the total volume, V, and we subtract this new little term, NB. That NB basically represents the total volume that the gas particles themselves physically occupy. And just like that, the V in our formula isn't the volume of the whole container anymore, it's the actual available free space the particles have to zip around in. So much better.
All right, next up is the second lie that these particles just totally ignore each other. No, they don't. They have these weak little attractions, right? We call them intermolecular forces. So imagine a particle just about to smack into the wall of its container, while the other particles behind it are kind of pulling it back, just a tiny bit, like a little game of tug-of-war. And what that means is, it hits the wall with a little less oomph than it would have otherwise.
So the crucial insight here is that the pressure we actually measure on the outside is a little bit lower than the true ideal pressure on the inside. So how did van der Waals fix this? He added a correction term right to the pressure variable itself. This new term, with that constant A, mathematically adds back the exact amount of pressure that was lost because of those attractions. And with that second correction, his masterpiece was complete.
So now we have our two equations. We've got the simple, elegant, ideal gas law, and we've got the more complex, but way more realistic, van der Waals equation. Let's put them head to head. It's time for a showdown.
This table really just perfectly captures that classic trade-off you always see in science. You want simplicity? The ideal gas law wins, hands down. It's easy. But you want accuracy? Well, the van der Waals equation is way, way better across a much wider range of real-world conditions. And that pretty much defines when you use them. The ideal law is for quick, back-of-the-napkin estimates, while van der Waals is what you pull out when you need precise, accurate calculation.
And you can really see that trade-off right here on this chart. As conditions, like pressure, start to get more extreme, the predictions from the ideal gas law just start drifting farther and farther away from what actually happens. But look at the van der Waals equation. It stays so much closer to the true observed behavior. When accuracy is the name of the game, there is a clear win.
Now, this is more than just a better formula, okay? It was a fundamental shift in how we actually understand matter itself. So let's talk for a second about why this equation really truly matters.
All right, so let's just recap the big ideas here. Number 1, gas particles have actual volume. Can't ignore it. Number 2, they attract each other, and that lowers the pressure we see. Number 3, the van der Waals equation is the clever fix for both of those problems. But honestly, the most important takeaway might be number 4. This whole story just shows science doing what it does best. It's this constant process of refining, of taking a good model and making it even better.
And trust me, this is not just some academic exercise. Think about it. Industrial chemistry, where engineers need to know precisely how a gas is going to behave under thousands of atmospheres of pressure. Or what about atmospheric science, where the accuracy of our weather models literally depends on getting these little details right? In fields like those, a good enough equation just doesn't cut it. Getting gas behavior right is absolutely critical, and the van der Waals equation makes that possible.
So we'll end here. Van der Waals gave us a massive leap forward, a much, much better model of reality. But the journey of science is never really over, is it? It always leaves us with the next fascinating question. What subtle forces or complex interactions are our current models still overlooking? And what will the next great equation for gases even look like?